Um, so this is going to be sort of a long-ish talk about operating systems. And first thing is that sort of disclaimer, this is in no way is this a complete guide to operating systems, because operating systems, as you know, I'm sure, are very complex and very sort of big things. Um, Now, what we're going to try to do is we're going to try to look at how we can get started in that domain if you so desire. And it's also um, it's also sort of not a guide to OS theory. There's a certain part of operating systems which you study in college, which is operating system theory of how do how do things like schedulers work, how do processes work, etc., etc. This is not going to be that. Okay, we're going to look at a more sort of practical-ish aspect of these things. And two things. First of all, if you have something you want to say or ask or whatever, just say so, because I can't see you. So if you make some sort of gesture, I can't see it. Um, and also that, yeah, I hope you can sort of ask things. Uh, yeah. Anyway, so we'll start by some like talking about what this whole thing is, and then we'll move on quickly to trying to write a sort of simple-ish kernel. What is an operating system? The basic definition, which you find in books and all that, is that it's a piece of system software. Now, the system software in itself is a big topic, but it's supposedly a piece of system software that manages your hardware. It lets you interact with your computer in an easy manner. That's the simplest definition. And it'll also give you certain nice features and services and all that. Right? Otherwise, managing a computer, as a user, managing the entirety of the capability of a computer is very hard for a one user, and the OS does that for you, right? And there are lots of parts in this operating system world. There are lots of sort of modules that sort of are layers one on top of each other. The most basic layer is the kernel, which you obviously heard of, and every um, every kernel is essentially a set of tools. It's like a library that you use to interact with your hardware, and it will provide certain nice functions, certain features which give you these basic things like ability to allocate memory and ability to look at chunks of storage as files and all those things. Kernel will do that for you. And related to the kernel is a file system. A file system nowadays is very important because um, kernels, in the early days, kernels and file systems used to be sort of different entities. And like for the very early machines like the PDPs and the Commodores and all that, you didn't really have a kernel, but you had a file system, and that file system let you interact with your storage devices and all that. So this is something that lets you look at a block of storage or a block of data as files, right? And then there are processes. Processes are sort of ways of managing running programs. There are drivers which let you talk to hardware. There are advanced things like the schedulers in operating systems like Windows and even in Linux. Schedulers are very complicated pieces of software because they essentially decide what happens when, and it'll decide which process should get runtime based on what parameters, and when that time should be taken away and all that. And then there are the cosmetic things like the desktop environment, which you interact with. And these are some of the things. And then we will start talking about how the boot process works, meaning how do you get, like a computer, when it is turned off, is just, it has no concept of programs, no concept of files, programs, etc., etc. It has no idea about all these things and where they exist, what even are they. So the boot process is meant to get you up to a certain level of abstraction, meaning that you should be able to interact with your computer by writing simple pieces of code, right? So the first thing that we need to talk about is the firmware. Every board, like every computer board, has some firmware built into it. And uh, for your typical computers, this is inside your chipset, your BIOS, UEFIs. These are very basic programs that will essentially just look for an OS somewhere, look for a kernel somewhere, and try to load that into memory. And that's all they do, right? At the very basic level, that's all they do. And yes, nowadays UEFIs and BIOSes have become quite elaborate with lots of GUI applications and all that. So this is the first thing that the computer starts running, the firmware. And that firmware looks for a bootloader. Now, a bootloader is something that it's very simply, it's a program that is meant to get your kernel loaded into memory. And it does a few other things as well, but its main job is to start the execution of the kernel. And that's all it does, right? And a typical common example of a kernel would be something like grub. No, not kernel. I mean, bootloader would be grub, and grub loads kernels like macOS, like Linux, like BSD into memory. And then when that is done, you are in a sort of space where there is nothing, right? Your system is not doing anything right now. It's the CPU is just running, right? It's essentially spinning, right? What you need to do now is start doing something, and that is the job of something called an init script. We'll come to that when we start writing some code. So, yeah, a quick thing about disks. Disks even today are sort of laid out in the fashion that they were ages ago. With SSDs, with solid state storage, there is no actual spinning device. Like there's no actual sectors in memory. It's just one long continuous piece of storage. But even today, disks, even SSDs and all that, they pretend in a way to be those spinning disk support. And there are these sectors or partitions in these disks. The first thing that it reads is the master boot record, which is MBR. We call it MBR. In most programs, we call it this. This is essentially a table of contents of what's where. And then there is the boot partition, the user partition, and the free space, etc. These are just a sort of arrangement of where things are. And this differs from operating system to operating system. Linux lays out its partitions in a different way, Windows does it in a different way, etc. So let's now start um, looking at some actual code. Okay. Um, what we'll do is we will try to implement a very simple, very basic kernel, right, which can at least get uh, something to display on a sort of simulated screen, right? Now, we won't do this for the x86-64 architecture. Reason, the boot process for an x86-64 processor is quite complicated. It has sort of levels to it. When your 64-bit CPU starts, it starts in a 32-bit compatibility mode. Then you need to check a bunch of flags, a bunch of settings to get into something called long mode. Long mode is your 64-bit address space. Even after you get into that, you have to sort of fiddle with privilege levels and all that. So we won't get into all that. We will start writing our operating system for a simpler architecture, which is ARch64, which is the 64-bit version of ARM. Essentially, this is a kernel that can run on a Raspberry Pi. Uh, why Raspberry Pi? Because it was just something I sort of felt interested in, being able to run sort of a kernel on this little piece of hardware. So let's uh, let's start doing that. Okay, um, we'll go to this. Okay, hopefully you can see this. I'm on my desktop, and I will just remove this old folder. Okay. So what we're going to do is um, start writing this in Rust. So for that, we're going to need to use the Rust package manager, which is Cargo. And so what we'll tell Cargo to do is create just a new project called OS. Okay, and it has done that. And we'll go to OS, and we'll remove the Git repository. Okay. So now we are in this sort of new Rust project. We just have our cargo.toml and our source folder. First thing we will do is go to code because it'll be easier to look at what we're doing. Now, yeah, in there. Now, arrange these windows. Okay. So, um, let's look at the main.rs file first. Okay, what it is, it's just the main function that I'll create for you, and it just sets hello world. Now, the problem is we have the first thing we need to tackle is we need to get when we are at the bare metal level, right? You cannot start executing Rust code from nothing, right? Because every language like C, C++, Rust, Java, etc. Every language has a standard library, and that standard library needs to be compiled for the target that you are targeting. But the problem is that we are not running in an environment where that can be compiled. So what we're going to need to do is first tell Rust, A, we don't want the standard library, and B, that we don't want a main function. Rust, like a couple of other languages like C, C++, etc., it requires a main function to start execution of code. And that is what it will look for. And it has to be in a very particular format, and we don't want that, so we will tell Rust to get rid of those things. So uh, these are what's called attributes, and we will set a no std attribute and a no main attribute. No main attribute. Now this will start giving us an error, and the error says that unresolved macro print line. Print line, of course, is a macro that's defined in the Rust standard library, so we can't use that, and we need to implement our own version of that. And yeah. So for now, this will not work because there's nothing that tells the CPU to go to this function, right? So for that, what we need to with is we need to write some assembly, okay? And if you don't want to get into assembly or sort of uh, averse to it, then look away for a moment and I'll just put some assembly into this file here. Okay. The first thing we do is create a section called text, um, and we define this label start. Now, I'm not writing the whole thing out because otherwise it'll take too long. I'll just paste in things, right? So, and if you want to ask something, and if you can just ask, and I'll reply right there. Right. So we've created a label called start. What this does is essentially the processor that's in a Raspberry, the BCM 2387, I think, something like that. So that processor is a quad core processor, and we we can't do multiprocessing yet. So we will make this process a single thread processor by halting three cores and just running on one core. And for that, what we do is just we check if we are on the right boot code, because this assembly will be executed by all four cores at once, and every core has its own boot ID. It has this ID. So we check that ID. If it's the right ID, we continue. If it's not the right ID, we go into this parking loop, right? Parking loop is just, it's an infinite no. And yeah, that's it. So the boot core ID will be, what we will look for is this binary 1 1 and ID mask. Uh, then we will start our, we will initialize our RAM in the PSS section. There is a section in every executable file which is laid out in a particular format, like in the ELF format. There are sections. There is the text section, the data section, BSS section, and so they have their own functions. This text section is where our program is stored, and the BSS is where our initial variables are stored. So we will initialize that with this. This address relative is a macro that we'll put up there. Okay. What it does, we don't need to worry about. Essentially, what this little piece of code does is that from BSS start to BSS end, it zeroes out the RAM. That's it. Uh, and then BSS init loop. This is the actual loop that does the initialization. And yeah, now we have after this little thing, we have essentially reached a point where we want to now initialize Rust. Okay, so we will create a label called init Rust, right? And we will put the, okay, let me explain this. This program takes up some memory, okay? And the BSS section has, it has starting and an ending, and we need to put the address of the end of the start of this program, right, before the stack into X0, which is the A register in ARM. So if you don't understand this, don't worry about it. Doesn't matter. What we're essentially doing is just starting Rust, right? Uh, then we, here what we're doing is moving the address of X0, which is the start of our program, right? X0 contains currently the start of our program into the stack pointer, and then we go to B Rust, B start Rust. B is essentially jump to Rust, and this start Rust is a label that will not be defined in this assembly file. It's an external uh, label, and this label we will define in our Rust code, right? And then Rust and what, the assembler in this case, they will link together these programs and make one continuous file. Essentially, what we're doing is cross compiling, and then we'll start put this size variable here to tell it how big this assembly is. Okay, that's our assembly done. Uh, we don't need to look at it anymore. It's just okay. Now, to help us build, first thing we need to do is create a makefile, right? A will makefile will help us sort of build this thing quickly. Um, I won't explain again, looking at the time, I won't explain everything that goes on in this makefile, just the simple things. So this is the makefile I made for this. The first thing we need to do is look at is, it's just a simple thing. It's not that difficult. Um, this program, AR64 null elf GCC, it's essentially a AR64 assembler. None is a target, which we don't need to worry about. None, it's none here because we're not compiling for a particular OS. ELF says that the output file, the binary that you make, should be in the ELF archive format. and GCC says that use the GCC compiler. And these are the arguments to it. We give it our target CPU. Uh, this we don't really need, it's for tuning. We tell it that we want little endian syntax for our memory, and there is this bug fix argument that we need to add to it, which don't need to worry about that. And so this will assemble our assembly file into an object file, right? And we do that with make boot, okay? And it has assembled our bootloader. So we had in our boot folder, we had this ar64.s file, which was the assembly. And now we've created this ar64.o, which is an L64-bit LSB. LSB means little endian um, executable. Now we've created this executable, but we needed to also work with Rust, right? So essentially what we're doing is using this program that I mentioned here, to compile the assembly, then using cargo to compile Rust, and then using Rust C to link them together. Okay? How will we do that? So for that, first thing, we need to add another file called Rust toolchain. So this is what tells cargo um, what targets to use, what sort of compiler to use essentially. So, um, so we have to give it the nightly channel. Nightly channel essentially allows us to use some features that you can't use on stable Rust because cargo keeps changing all the time. Like if you install cargo today and then use it a week later, it will have changed in that time. Anyway, um, essentially what's important here is that we're telling it we want the AR64 target, means whatever your source code is, compile it to the AR64 target instead of the x86 target. Okay, that's it. Um, that's that's all that does. And now what we can start doing is writing our linker script. Again, this is something that if you don't want to look at it, don't look at it. It just tells uh, it just tells the linker which we will write. It just tells the linker where to find your memory. Like it tells the linker the memory layout, right? This is just a file that does that. So we'll quickly go over it. First thing, load address. If you've done a microprocessor course, you'll see this address quite a lot there. Your initial sort of load point is this address. So uh, our load address is this, and this is telling the linker that the entry, meaning the first instruction of this program should be loaded at this address. Okay, and this, why is this particular address and not some other address? It's because the Raspberry, every board needs to have its own thing like this. Okay, the Raspberry has a firmware inbuilt closed source which just places your kernel at this address. So that's what we're going to do. And then we're going to tell it some other things as well, like keep the text section, meaning to keep the code, keep the arguments, all that. This, again, doesn't matter. It just helps us compile. So if you don't want to look at it, don't look at it. It doesn't matter. Uh, I'm skipping over all this because this is not the actual like the code that we need to look at. So anyway, now I think we are in a state to start building. Okay, let's go back to the main function. And let's rename this function to start Rust. Okay. Um, why did we rename this to start Rust? Because in our assembly, we the told the assembly to jump to this label, and this label will be found here. Okay. Now, in order to find this label, it has to be non-mangled, meaning most compilers, when they compile a source code, any file, they change the names of these programs of these functions to something that helps them debug. they mangle the names of functions essentially. Otherwise, functions are just labels with this particular name. And so what we're telling Rust C is just don't change the name. Okay. And now if we try to compile with make build, we'll get an error. Uh, we don't have this feature. Okay. So what we want is, first of all, in our cargo toml, we need to add certain dependencies. And again, this is not that important. It just helps us build. So profile, release, default features, these are just Rust specific things, so we don't need to worry about. What we need to worry about is these three dependencies. We depend on this library called top registers. It's essentially an assembly. It's essentially an embedded version of uh, of something that Rust provides internally, but it doesn't depend on the Rust standard library, so that we can use it. And then there is this Cortex A library developed by the same people, um, which lets us sort of structure our processor registers in a nice way. That's all it does. Just gives us those names. And then aligned is just a library I added for aligned memory allocation. Anyway, uh, what else do we need to do? We need to add a bunch of features for our main. Now, these features, what do they do? First, allow assembly, allow global assembly, and these, let's not get into those. Doesn't matter, we're running out of time. So let's now try to compile and see what happens. It's compiling the libraries. Okay, good error. Now it says we don't have a panic handler. Now Rust requires that every program that is compiled should have a panic handler, meaning that if the program exits unexpectedly or has unexpected behavior, essentially panics, then there should be a function to handle that. Okay, what we're going to do is we're going to create a module for that. We're going to call it panic9f because that's what I have, and do quick fixes and create this module. Okay, it created a module for me, and what I'm going to do here is what's the important bit is this. Uh, the important bit is this, right? So we're telling it whenever a panic happens, go to this function and do these things, right? Uh, what does this do? It will just print that the kernel was spooked by something, which we'll get from the arguments that this function is given, and then we'll halt the CPU. Essentially, whenever something bad happens, print this, stop execution. That's all, right? And it gives us a few errors for modules that don't exist yet, but we're going to create those modules presently. And then what we need is a way to print. Okay, we need the first thing we need is a way to interact with this kernel. How do we interact with this kernel? We cannot use the graphical interface because there is no graphical interface yet. We want to use the serial interface. Okay, um, I what I will do, looking at the time, is I'll just copy this entire folder here. Okay, and actually module for it. BSP stands for both support packages. Essentially, what I've done in this is that I've implemented a few device drivers. The important device driver for us right now is this UART driver. The UART is a particular chip on the board that speaks a serial protocol. That's all. And we will emulate this program in a way that lets us read this serial output, right? Because we don't have a screen yet. Okay. And these are just the registers that we need to read and write to these registers. There's a lot of code. If you want to look at it, I'll give you a repo that you can look at. Um, Essentially, what we're doing is we're reading certain registers, right? We're reading certain registers, checking if they are in a particular state, and then writing. to a particular address, which is the memory map address of that device. That's all. If that doesn't make sense, again, don't worry about it. We can look at the code later. Okay. I'm going to copy over some modules. Print thing. These are some modules that simply just like the CPU module provides us a couple of functions to halt the CPU or to spin the CPU. Um, the driver, it just provides a type that all device drivers should follow. It's an interface that all device drivers should follow. The module. Print module is just an interface with the serial console, whatever serial is. Serial can be the GPIO, it can be the UART or whatever, right? It just writes to that serial and that's all. Okay. Um, what else? Okay, we didn't create these. So let me just create these modules here. And we don't have console module yet, but we'll do that right now. Okay. So um, so we'll look at this console in a second. Um, yeah, are we done? No. Okay. So um, how do we start our OS running? What do we write in the start Rust program in this function, right? I don't know. Why is it not found? It's right there. Oh, I'm not getting it. Okay, this is RLS. Um, RLS is panicking. Anyway, so what do we write in the start Rust to get our code running, right? Um, these modules that I've just added, they contain some functions that will help us interact. The details are not important. The idea is to quickly get through this. Okay. So the first thing we need to do is initialize our drivers. So we will use these grades. The first thing we will use is the driver manager from the BSP drivers crate, and we will iterate over all of our drivers, right? And we will initialize them, right? Uh, okay, yeah, I need to create an unsafe function for this. So since driver initialization can access random memory locations, which Rust is not okay with, we need to make this function unsafe. Okay, and we also need to, you make public but unsafe. Okay. We need to tell Rust that this function either itself does something bad or calls a function that does something bad. So, so that it doesn't panic, right? What does it want here? Okay, yeah, we're not returning and panic yet. Okay, so after our drivers are initialized, what we can do is make a main function, right? This is just a name we are choosing on our own. You know, we can call this function anything we want. Don't have to call it main, and it should return. We'll call this function. So what's happening here is we are initializing our drivers, right? And then we are jumping to a safe function main, right? And there's this on initialized function that I made in the manager, which does something after code has been initialized. Yeah, that's about all we need to do here. And then in main, what we need to do for now is just loop infinitely. Okay. And then let's see if this compiles. Okay. We make good. Oh wow, it compiled. That's great. What this compilation did, let's look at it again, is It assembled the bootloader, compiled the kernel, and linked it with the bootloader that we had built with assembly, right? And this gives us an executable that you or another emulator like QEMU can execute. So to test that, what we're going to do is we will write a print, a simple print of before the loop. We use the console crate, which we haven't used yet. Let's just copy that out. We'll use the print line, which we have implemented ourselves in the print module. Where is it? There. And this is just a copy from the actual Rust, you know, the original Rust macro. So it's nothing special. So let's try to run this and see if we get hello world. Like, right? Okay, make and these are all targets that are in the make file. If you want to look at it closely, we don't have time to go into it. But okay. Oh, now you can't see this. But you can see hello world came up. Where did this hello world come from? Uh, you can see the run Kimu command. What it's doing is it's running the AR64 version of Kimu with a motherboard of type Raspberry 3. And it's piping the serial output to our standard in. It's using the kernel that we built. And so after that, whatever appears on our standard in and whatever appears on our standard out is coming from our written kernel. So that's cool. Okay, now let's use some actual UI, right? Like use some of these functions that we wrote in the console crate. Now this console module or whatever, it has some functions that help you interact with the video memory. So what they do is essentially just write directly to video memory, and this will let you clear the screen, write something to the screen, or read something from the screen. And that's where this console module comes in. I've written this little text thing that lets you write text directly to the video memory. And there is a font that we render every character as a particular glyph, and that comes up in the video memory. So we can write hello world to the screen, right? Let me say hello world. We don't have an exclamation mark here, but and we don't have a comma here. So let's compile that. And you can't see this, but let me. Okay, now I'm sharing whole screen. So when I run make Emu here, it comes up with hello something world because I don't have glyphs for W and R yet, but it comes up with hello world in QEMU. So what this is our code running on an emulator on bare metal, writing to video memory and showing us hello world. And this is sort of the most basic you can get with a kernel, right? You can write to the video memory and then show that to the screen. So that's this, right? But we're not satisfied with that. We want a fully fledged kernel, right? We don't want to be writing sort of assembly and Rust all the time and writing our whole kernel from scratch. So we want a fully fledged working kernel, right? So let's do that. We have now, because we are an operating system, we know that we have a running kernel in our system, right? Linux is running on this system. So let's get Linux to run our code, right? Because what Linux does, like every other OS, like every other kernel, is it will first initialize the kernel and start running your code, which is the initial init script or the init program, right? For normal Linux, this is usually systemd or another init program like that, but we can make it run our own code. So let's do that. Let's create a directory or let's not create it. Let's go to this directory that I have here. Okay. Now, what I have here is a this is an executable of my own kernel, right? What you can do is you can find this inside slash boot, and there's your kernels right there at the bottom. You can see these are the kernels that have been on your system at some point. So these are all in the slash boot folder, and the slash boot folder also represents a boot partition in your disk. So essentially, these are in your boot partition. So what we can do is we can get this to run our code, right? So what we're going to do is we're going to let's 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 write a simple C program that Linux can run, right? So um, we just write hello world and main. Don't need the arguments, so we won't bother with the arguments. Why am I sleeping for a long time instead of just returning? Because uh, when this program gets executed, Linux will execute as it as PID1. And in Linux, PID1 should never exit. If it exits, the kernel panics. So we're not going to do that. We're going to try to sleep for a certain length of time. Okay. And what we can do here is just say printf hello world, right? And slash n. Okay. Now we've written it to this C file. We will compile it with GCC, and we will put the output in a file called init, and we'll tell it that compile link it statically, meaning link the entire glibc, meaning the GNU standard library, into this statically. Okay, compiled again. This always happens. Anyway, so now what we have is a file in it, which is a statically linked LSB executable, right? And now what we want to do is get Linux to run this. How do we get Linux to run this? Well, first we need a file system. How we get that file system, not really important, but let's just go over it. There's this archive format called CPIO. Linux started using this way back in the day. Um, Instead of using tarball or anything like that, they opted for this because it was simple. So what we do is essentially file, pack our executable in this CPIO format, and tell Linux that this is a disk that you should mount, right? It'll mount it as an initial RAM disk, and then look for a program called init, a program literally called init. And when it finds that program and it has the executable bit set, it will try to run that program. Let's do that. Uh, Easiest way to run this program is um, to have, okay, so we're writing some blocks to a file called cpio.gzip, and then we will get QEMU to run this, right? We will, oh, what is this? Okay, yeah, we'll get QEMU to run this. So what we're doing is telling QEMU, this is the kernel to use, the Linux kernel that we just copied from our own system, right? No graphical user interface yet. Don't reboot. Like if the kernel inside tries to reboot the system, don't reboot, just exit. Initial RAM disk is our cboot.cpr.gzip, which we made ourselves, and we're telling it that if you panic, just exit with code one, and the console, meaning, okay, this is not important, but this just lets us see the output on our own console. That's all. Okay, and starting that, you'll see a typical Linux startup procedure, and there's our hello world. So this is Linux, the kernel Linux, right? Not some old, not our own kernel, uh, 5.14 that too, running our init script inside Linux, right? And this is how, like, this is the point where system D would take over, right? System D is a init daemon which would start from this point and initialize the entire system for you, right? Now, this, of course, is not that useful because it doesn't really do anything. It just says hello world. Instead of this, what we can do is, okay, yeah, we can't also exit because there are no interrupts yet. So the kernel can't look for, right? The kernel can't see our control C. So we have to do kill all and yeah, kill it. Okay, so um, so what we can also do is instead give it a set of standard binaries, right? Now, I don't know if you've heard of BusyBox. BusyBox is a set of binaries that, uh, well, it's basically it's this one giant binary that has a lot of command line utilities inside it, right? So what we can do is we can tell, just a second. Is it okay if we, I don't know, well, because I mean, I don't want to lose the time, but is it okay if we go slightly over time?
Marcelon is not here. He left. So I
Oh,
guess.
okay. Okay, well, okay, if it's okay with you guys, then.
Yeah, yeah, I'm fine.
Um, all right. So BusyBox is this set of command line utilities that essentially gives you things like binsh, like the shell, the cat command, the ls command, the make directory command. It gives you all these in one single executable, right? And it creates these symbiotic links to that executable so that you can call various things. So essentially, this is like GNU core utils, if you've heard of that. So your computer has some basic utilities like sh, like cat, like ls, like mkdir. Like these are basic utilities that you know need to do anything, right? So every distro has its makes this choice. Every distro makes this choice that which command line utilities we want to include by default, which of these packages we want to use. So BusyBox is just one of those packages, right? And there's another one called Toybox, which Android uses. Android, by the way, if you didn't know, is also Unix. It's also Linux. Just it just you know runs everything inside a JVM instead of running on Linux. So anyway, so what we'll do is we'll just clean this. We'll just do a make clean. Remove this folder that I created. This is the stock version of BusyBox that you get from GitHub, right? And you can even check. Okay. So what we can do here is, first of all, we can compile BusyBox. We can compile this statically linked and then get our Linux kernel to run this, right? Instead of the program, the init.c that we wrote. So to do that, we can just, it's very easy. We can just use the make file that's inside BusyBox. We can tell it, first of all, make that config. What this does is just it creates a sort of configuration file to use. And then we can tell it make uh, this. Yeah. So we will tell it that we want to statically link it. And this J thing, it's like this multiprocessor command. We can also say nproc here, number of processors. Nproc is just a command that tells you how many processors you have. So what this will do, it starts compiling BusyBox. And there it goes. It's using CC. Um, and now it's statically linking. Okay, now it has built. Now, what it did is that it built these two files, BusyBox and BusyBox unstrip, which we can check. They are statically linked binaries, LSB executable again. So now what we need to do is we need to pack this into a format that Linux will understand, right? And to do that, we use another make command, which is this, right? We'll install it into a directory, let's say, OS. Install, what this does is essentially it just creates these symbiotic links, lots of symbiotic links called sh, cat, etc., all pointing to the same binary. And I think this has a bug. It sort of does something wrong, which I'll need to fix, but don't worry about that. Um, we'll create this folder called devos, and it'll put all these binaries. Do you see how it created these symlinks to our BusyBox? All of these are symlinked to BusyBox. Okay. Um, Now there's a problem with this that BusyBox becomes dynamically linked for some reason, so we need to compile it just once more and then copy it over. Static, uh, OS, BusyBox. Okay, so uh, we created this directory called devos, right? In this, we have a bin as bin and user directory. This is the typical bin sort of root level folder structure that you'll find in any Linux system, right? And there's this Linux RC symlink. What this is that in the ancient days of Linux, there used to be the init script in Linux used to be called Linux RC. So today this is called init, or which sort of points to systemd. But anyway, point is that it's called something else because this BusyBox is a pretty old system. So it's called something else, but we can fix that. That's not a problem. So what we'll do is, again, we'll pack this into the same CPIO format that we did with our old file, right? Oh, not file. We'll pack this entire folder. That's what this is doing. A find dot, pack it into CPIO with this format. Put the output, pipe the output to gzip and put it in, let's say, it's called dboot for BusyBox boot in this file. Okay, and it wrote a bunch of blocks. Okay. Now, now what we want to do is get Linux to run the BusyBox that we just built. Okay, so what we'll do is for that, no, no, that's not one. Okay. Okay, so we'll just run Emu the same way that we did for our own init script, right? We will run Emu with the same Linux kernel from our own system. We'll tell it the initial RAM disk that you should mount is bboot, which we just built, and this append, what this is doing is essentially it's giving these arguments, these command line arguments to the kernel itself. So now what we need to tell the kernel is rd init equals bin sh. What is this? This says instead of looking for a file called init to start executing, right? Instead of looking for that file, look for something called bin sh. What this will do is it will not initialize the Linux system. It will simply give us a prompt. Let's see if it works. Oh, we call it boot. Can we call it boot? It's oh, we didn't. Okay. Boot.cp. Okay. Put it in I put it in the wrong directory. Anyway, so once again, run that command, give it the run disk, and tell it to start running bin.sh. Let's see if it works. There's the kernel. Okay, run bin.sh as init process. You can't access a TTY. TTY stands for the teletype, by the way. And then press enter. There's a prompt. We are inside, we are running a Linux on QEMU, and that Linux is running bin.sh. This system hasn't started yet. It has no conception of anything, right? It has no functionality yet, but it's giving us a prompt. It's just running the kernel, giving us a prompt. That's all. Now, typical Linux systems, what they will do is they'll have a init daemon at this point, like systemd, system5, or you know all those things. What they will do is start the network, listen for drivers, initialize your hardware, and do all these sorts of things, and set up your entire system and give it to you as an interactive thing. And system D by itself, it's a daemon, so it will essentially it listens for changes to the hardware as well. In the olden days, it didn't used to be like that. So the init script would come, run, and go away. But then systemd, became this persistent thing that's always running. Now, we can even see that it has things like ipconfig. Oh, sorry, not ipconfig, ifconfig. We get an interesting error here as well. Um, Processes on a Linux system are they're inside this proc directory. Um, the proc directory is not actually a directory. You know how people say that everything in Linux is a file? That's not really true. Okay, some directories, some files are essentially false files. They don't exist on they don't exist on a disk, they don't exist in the RAM. They're just hallucinated by the driver. They're just made up, right? And proc is one of those things. So an init script, what's in it, something like an init script would do, it would create a proc directory, and then it would um, mount proc, 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 there, proc, proc, proc. Uh, okay, anyway, so point is that it would essentially mount that directory as the point to start putting your processes in, and then when you can start putting your processes in that directory, then you have a functional Linux system. And yeah, so that's essentially basically is there anything else if you anyway, so if there's anything you want to ask, I'll be happy to answer your questions. Also, if you want to see the code, I can give you a repository which you can look at. Also, if you want to see some references, there are a few references, like there's these talks on YouTube. If you want to see, um, you know, if you want to see some references, you can look at those. They're nice talks and good things. Also, another reference is um, if you've heard of the LFS book, the Linux from Scratch book. That's this, that's this online document that tells you how to build a Linux system. It's pretty big.